And you get 0 over 0, correct? So what was the problem? You removed the problem, because if you did not remove the problem, you didn't get the answer. So what did you remove eventually? Exactly. X minus 2 is the problem. That's why we got 0 over 0, because of x minus 2. Although 0 over 0 does not guarantee that the limit exists, once I removed the problem, I got the limit. Okay, good. Did we have any problems with this? Any problems? Do I need to show this or anything here? Yes, please. Number 3? Okay, so let's take a look at number 3. So this is done. Will I consider it done? Okay, so let's look at number 3. So we have limit as x approaches 2 from the left from x squared minus 2x divided by x squared minus 4x plus 4. Okay. So I plug it in. 4 minus 4, 0. 4 minus 8 plus 4, 0. So in this situation, there is hope, right? There is no guarantee, one more time, but there is hope. Good. So I'm going to try to do the same thing, which is what? The same thing. Exactly. I know there is a problem, for sure. Which is the problem? Hopefully I can remove it for good. If I can remove it for good, then it's going to be okay. I get a number. But if I cannot remove it for good, especially from the denominator, of course, then the limit does not exist. So which is the problem that I'm trying to remove? Of course, again, the same thing. So I factor the numerator. How? And I factor the denominator. And how?
X minus 2 times x minus 2.
Very good. So x minus 2 squared. Very good. So one factor goes away. Here it is. However, when I plug it in again, I get 2 at the top, but 0 at the bottom. So as I mentioned before, 0 over 0, there is no guarantee. It turned into an undefined case. So now I know the answer. It's this, or this, or this. Unlikely for a rational function to be this, because it's from one side. So I will plug in 2 from the left, which is 1.9. Positive, and here. So the answer is? Very good. So this is done. This is the same problem with the one that we just did a couple of minutes ago. Oops. Any problems with number 10? Any problems with number 10?
Yeah, can you do that?
Yes. So we have limit as x approaches 2 from 1 over x plus 1 multiplied by 2x to the 4th. We could use the limit laws here. This is a product of function f and function g. So I can write limit as x approaches 2 from 1 over x plus 1 times limit of 2x to the 4th as x approaches 2 from either side. But I can do this only under a very important condition. What is the condition? What has to happen in order to be allowed to apply a limit law? Please.
Both the limits have to exist.
Exactly. Does the first limit exist?
Yes.
It's 1 over?
3.
Yes. How come? Because 2 is in the domain of this function. Does the limit of the second one exist?
Yes.
This is a polynomial. How do I find the limit of a polynomial?
Always exists.
Just plug it in. So the first one is 1/3. And the second one is
32.
32. So this is 1/3 multiplied by, if you want, 32 over 1, so it's 32 over 3. So this is a situation in which it was very straightforward. I didn't have to do anything. I only had to use the limit law and find the limit of a ratio that had 2 in the domain, and the limit of a polynomial, which never ever gives headaches. What about this one? Number 12. Did we get number 12? Yes? What was the limit?
That's not exist.
Right, because you determined the limit as x approaches 2 from the left of 4 minus x squared, and you determined the limit as x approaches 2 from the right of x minus 1. Both polynomial,
0.
straightforward. The first one is 0, and the second one is 1. So therefore, the limit from either side of f of x as x approaches 2 from either side is
Does that exist?
any. They're not the same. Very good. Okay. Now I would like to talk today about number 7. Yes, please.
Just click on 6. I was confused because.
Which one?
Number 6.
Okay.
Just kind of wanted to double check because there's a radical there that doesn't get factored out. So you can have both negative and positive square root.
Right here. You mean you're talking about 5 or 6?
6.
You're talking about this one?
Yeah, that one.
It's this one with 1 and 1.
I got, yeah, well, not as like we talked about, where you just assume it's positive. Okay. Yeah, okay, here it is.
Okay. So limit as h approaches 0, the square root of 1 plus h minus 1 divided by h, as we discussed, is 0 over 0. So I will multiply by 1 plus h plus 1. The square root of 1 plus h plus 1. Agreed so far? So then the top becomes 1 plus h minus 1, and the bottom is this. These two go away, h's go away, so it's 1 divided by 2. Is that better?
Yeah, it's just, well, you could have plus or minus 1 is the square root. If you're just plugging in, just purely plugging in the numbers.
You mean when you plug in 0 in here?
Yeah.
1 plus 0, the square root is not plus or minus 1.
The square root of 1
The square root of 1 is 1.
or negative 1.
No, very good, very good. We need to talk about this. Because I know where the confusion is coming from. Okay, so if you want to solve the equation x squared equals 4 by taking square roots from both sides, the correct step is the absolute value of x, because the square root of x squared is the absolute value of x. And the right-hand side is 2. Now, this equation says, how many numbers have distance from 0 exactly 2 units? How many? Negative 2 and? Correct. So that's why we get negative 2 and positive 2. The signs of positive and negative do not come from this side. They come from the absolute value. The square root of 4 is only 2. We tend to omit this step when we use taking square roots. And we write directly x equals plus or minus 2. And many students get confused with that, and they say, oh, the square root of 4 is plus or minus 2. No. The square root of 4 is only 2. The opposite square root of 4 is negative 2, which has nothing to do with this particular problem. So the square root of 1 is not plus or minus 1. You can even put it in your calculator. Take the square root of 1. You will not get plus or minus 1. Ever. So that's why coming back to our problem, when I plug in 0 here, 1 plus 0 is 1. The square root of 1 is 1. 1 plus 1 is 2. Very good point. Thank you for bringing that up, because I wanted to clarify it. Good. Anything else? Anything else from this? Now, I would like to look at this problem. Remember, so far, I didn't forget, Joe, about the piecewise defined function. I didn't forget. We'll choose one in a minute. I asked you to commit to memory a couple of graphs so far. One of them was tangent with vertical asymptotes, right? And the other one was arctangent with horizontal asymptotes. Then I also said the log, right? Did I say the log? If I didn't, no, okay. So here's another function that is natural log x. We need to commit this one to memory as well, please. Here's the graph of natural log x. And here's another one, which is the exponential function. So this is natural log function. And this is the natural exponential. And here's the graph of the natural exponential function. These we have to remember. Can anyone tell us about natural log? What does it have specifically? I look at the graph and I say domain is, and it also has blah. What is the domain of a log function?
Not including 0 to positive.
Exactly. Open parentheses, 0 to infinity. Awesome. And what is specific for this function? What can you say? Oh, I see. It has a vertical asymptote at 0. Awesome. Vertical asymptote at 0. These two functions are inverses of each other. So now what can you say about e to the x? So I'm going to write here x equals 0 is a VA. And domain 0 to infinity. Now I would like, when we refresh our memory on this exponential function, what will you say about its domain? Of course, friendly function. And it has something very specific. Yes, but only at negative infinity. So y equals 0 horizontal asymptote at negative infinity only. At negative infinity only. Okay. So now we have basically 4 different functions that we have to commit to memory, because I'm going to add one more. I'm going to add this one right now. So we know tangent, we know arctangent, we know natural log, and we know the exponential. We're going to encounter these a lot. Any questions for me? Okay, so now let's talk about this function. First, we have to identify it. What type of function is it? Rational. It's the simplest possible rational function. There is no simpler rational function than this one. We call it the base function, the simplest possible rational function. Okay, perfect. Well, here's its graph, and we do have to remember it. We are going to use it a lot. Here's the graph. So now, if I ask you what is the limit of 1 over x as x approaches 0 from the right, you will say, very good. And limit of 1 over x as x approaches 0 from the left, you will say. And then we have to fill this in. the limit of 1 over x as x approaches 0 from either side, what will you say? Correct. It does not exist. Limit of 1 over x as x approaches 0 from either side is D and E. So please remember that. Okay. So for now, I would like to determine this limit. Then we are going to come back later to these. What will you say? And that has to be committed to memory. We discussed that for sure. 1. So that is 1. So that is also done. We're going to look at an example like this in a minute. We did an example like this, and we're going to do that again. And then we're going to look at this and this. Okay? And then continue. Ready? Before we look at these limits, maybe we should look at a piecewise defined function because I don't want to forget. So I'm going to try to find one, and I did. So let's look at this function. It's on page 108, problem 50. I'm just going to copy this function and graph it. And then we can answer these questions if you want. But we will sketch the graph first because that's what we want to practice. And then we can answer those limits. Okay, ready? Is this good enough? Okay. So here's the function, f of x, so g of x. So this is one more time, problem 50 on page 108. And this function happens to have 4 branches, 4 different pieces. Okay, the first piece, x, for x less than 1. Second piece, 3, for x equals 1. Next piece, 2 minus x squared, for 1 less than x less than or equal to 2. And the last piece, x minus 3, for x greater than 2. Obviously, it's useless to ask what type of function is this, but if I do, what will you say? It's a piecewise defined function. It has is made out of 4 different pieces. They will never overlap. Please remember, what we graph to the left of 1 cannot be graphed over what we graph to the left of 1 to the right of 1 or to the right of 2. Okay? Good. First, I have to determine what? Every time I'm asked to graph a function, I have to determine, this is mandatory for any function. What do I need to find first? The domain. So I start by picturing these and see what's happening here. If I replace this with an interval notation, what will that interval notation be? To 1 with a parenthesis. This is very clear. This is the point 1 comma 3. Not to be confused, so this is point. Not to be confused with an interval, right? So the function exists between negative infinity and 1, and it also exists at 1. Now on this side, the interval is with parenthesis, comma, 2 with a bracket. Awesome. And finally, the last one will be with parenthesis to infinity. And now let's analyze, because it's very important. If the function is not defined on all real numbers, then I have to present some gaps. If there are no gaps, then it's defined everywhere. So I see it's defined to the left of 1. It's defined at 1. It's defined to the right of 1 between 1 and 2. It's defined at 2. And it's defined to the right-hand side of 2. So I conclude that the domain of this function is very good, all real numbers. This is my starting point for my table. I have to present the domain in the table. Now I'm asking myself, which are the x values that even if I don't want them in there, they have to be in there. Mandatory, always. 1 and 2, and also 0. 0 is always in the chart. In this case, 1 is in the chart and 2 is in the table as well. Okay, now I look at 1. Be careful how I present the symbols here. Under 1, I will have 3. Immediately under 1, I will have 3. But then left and right, I will have 2 parentheses. Is this clear? So 1 comma 3 is here, but there is a left parenthesis under 1, and there is a right parenthesis under 1. Now, what happens under 2? Can anyone tell me what to present under 2? To the perfect. A bracket to the left and a to the right, and they are touching because there is no number in between like I had here. Now this is an overkill, I know, but I think it's safe if we put it in. Which function will I use between negative infinity and 1? X. Which function will I use between 1 and 2? Perfect. And which function will I use between 2 and infinity? That's it. So I have linear, and I have quadratic. It's also important because of the shape. So these two will be lines, but this will be a parabola. Okay. So now, let's plug in 0. Let's plug in 1. And I know you should say don't, because you are not allowed to. But if you say don't, then I'll have to ask you to plug in 0.9999999. And it will be very difficult to plot. So if we plug in 1, what do you get? 1. Let's plug in 1 on this side. The same thing. And let's plug in 2 on this side. Perfect. Let's plug in 2 on this side. Perfect. Let's also plug in 3 because it gives me an x-intercept. Good. That's all we need. Is this better? Joe, is this better? Do you feel a little bit better? Anyone else? Do you have any questions? Anyone? Okay. So now let's graph. From left to right, please give me the first ordered pair. Very good. The first ordered pair is 0, 0. Next ordered pair, please. What type of point is this? Very good. And I'm done with the first branch. Don't mention it again. And we cannot extend it to the right. Good. Please give me the next point in line. What type of point is 1, 3? Very good. Awesome. I'm done with 1, 3. I'm moving on to the next branch. Next point. Okay. Still open. It's this one. Good. Next point. 2, negative 2. What type of point? Very good. And this is a quadratic function with a maximum, so it has to look like this. Not a straight line. Okay, very good. Next. 2, negative 1. Open point. And then 3, 0. Straight line with a positive slope. And this is the graph of the piecewise defined function. And since we are here, let's answer these questions. So first question is, find the limit as x approaches 1 from the left. 1 from the left. 1. 1 from either side. Exactly. G of 1. Very good. Limit of g of x as x approaches 2 from the left, 2 from the right, and 2 from either side. Correct. Good. Anything else? Okay, so I'd like to go back to your book. I know I promised an example like this. I want you to work on this one. I'd like to choose another. And we are on page 107. And I would like to work on 44. Okay, and here's the limit. Limit as x approaches -2 from 2 minus the absolute value of x over 2 plus x. This is not a trivial situation. Here's how we start. We have to start by simplifying the function. We need to simplify the function. This is the function. I'm going to call it f of x. You can give it as any name you want. And I have to start with the absolute value of x. The absolute value of x itself is a piecewise defined function. So can anyone tell us how to express the absolute value using the formal definition of the absolute value? What can the absolute value be? Yes, please.
It would be negative x for when x is less than 0.
Perfect. And it will be x when
X is greater than 0.
or equal to 0. Very good. This is the correct definition. So the absolute value can be replaced by x for positives and 0, and it will be replaced by the opposite of x if x is negative. So that makes the absolute value always positive. Is this clear? So one more time. If x is a positive number or 0, this doesn't mean anything else but x. But if x inside is a negative number, we can remove the absolute value bars by replacing the absolute value of x by negative x. Because if it's negative times the minus in front, it will always make it positive. Okay? Good. So now I'm going here to simplify the function. So I want f of x this time, which is 2 minus the absolute value over 2 plus x. Because the absolute value has two possibilities, the function itself will have two possibilities. What is the first possibility? So the first possibility is when the absolute value of x is replaced by x. What will I have at the top?
2 minus x,
Over.
2 plus x.
Very good. For x greater than or equal to 0. Very good. Now the second option.
2 plus x.
Very good. Over 2 plus x, which is 1. However, I have to be careful. It is 1. But for what interval?
Less than 0.
Careful.
But not including 0.
Yes. What else? Look at the function.
Oh, and it's negative 2.
Correct. Correct. So I cannot simply write x less than 0. I have to write either as a domain with interval notation. That will be the best. Negative infinity to negative 2, union negative 2 to 0. I wanted to exclude it from here as well, but it's x is greater than or equal to 0, so there is no need to exclude it here. x greater than equal to 0 does not include negative 2. But on the second branch, I had to exclude it. Always be careful with rational functions. You can remember that I like to call them not friendly. We have to be careful. They don't always work for everything. Right. Okay, so now I'm ready to address the limit. I wasn't ready until now, but now I am. So, as x approaches negative 2 from either side, what function am I looking at? Am I looking at this, or am I looking at this? Is it the top branch or the bottom branch? Of course, this one has nothing to do with negative 2. It doesn't even exist at negative 2, right? The limit, the function doesn't have to exist, but it has to exist around the point. But this one, it has nothing to do with the function, with the limit that I'm looking for, of 1. Very good. So what is the limit? 1, indeed. The limit of a constant is the constant itself. Perfect. So for Tuesday, please work on number 2. Carefully. It's the same type of steps. You have to do the exact same thing. It's just that it's a different function. Okay. One more, and then I would like to look at the squeeze theorem. So I want to work on this, at the simplification one. So limit as t approaches 0, 1 over t, the square root of 1 plus t minus 1 over t. Ready? Okay. How do we address this? What do we need to do? Plug it in. I get in trouble from the moment I plug it in. Because it's 1 over 0, I don't have an answer, and it's 1 over 0, I don't have an answer. I cannot use the limit laws. I cannot say the limit of the first function minus the limit of the second function. Why? Because the limits have to be numbers. Otherwise, I can't use the limit laws. Awesome. So then there must be something else that I need to do before I even decide the action. Good. So I see 2 fractions. What can I do with 2 fractions that are subtracted? Subtract them. But how do I subtract 2 fractions? What do I need to do before I even get to that? Very good, indeed. So limit as t approaches 0. Notice that we couldn't even identify the type at this point because we couldn't figure it out yet. What will be the least common denominator? Of course. 2 factors, both of them have to be in the least common denominator. Very good. Okay, now what?
1 minus square root of,
Awesome.
1 minus square root of 1.
Thank you. Yes. So this is the same denominator. It doesn't need anything. But this one was multiplied by the square root. So this is my reminder. Don't forget to multiply the top. So perfectly correct. 1 minus the square root of 1 plus. Now I'm hoping that I can come up with what this limit is all about. Maybe it's just a number. Maybe it's 1/5. Or maybe it's 0 over 0. Or maybe it's 5 over 0. So now I'm ready to plug it in. So let's plug it in. What do I get at the top when I plug in?
0.
Perfect. What do I get at the bottom when I plug in? 0?
0.
Correct. So there is hope, right? It's an indeterminate case that could change into a number eventually. Okay, now I'm looking at the function. I say, oh, it's a rational function, but it also has an expression that is a radical, and it has a sum or a difference of radicals. Notice one thing. This is not the problem. I plug in 0, I have the square root of 1. So I will never even think of removing this or multiplying or rationalizing something that is not a problem. But that one is a problem, because when I plug in 0, I have 0 at the top. But this one is not 0. This is friendly. So then, what do I need to do? Like we did a few minutes ago. What do we need to do?
Multiply by the 1 plus square root of 1 plus c.
Very good. Awesome. Rationalize the numerator, not the denominator. I see a radical in here, but we're not bothered by this at all. This is 1 when t approaches 0. So I will copy the denominator. Because I can't do anything to the denominator. And now I'm using the special product that we discussed on the first day. Now I have to be extremely careful, because I have a squared minus b squared, and I have to distribute to this. So 1 minus, yes? Yes, I have to distribute -1 to 1 plus t. So be very careful. You don't have to do this in one step. You can write 1 minus parentheses 1 plus t, if that's better for you. And then distribute. So obviously these two go away. So this is limit as t approaches 0. The numerator is -t. And the denominator is t, the square root of 1 plus t, and 1 plus the square root of 1 plus t. Obviously, what will happen next is, right, and please write 1, not to be confused with 0 or anything else. And now, only at this stage, I will do what? Drop the limit operator. At this stage, I can plug in 0, and the limit operator goes away. Only when I plug in the number at the very end, the limit operator disappears. So then I'm ready, please. The top is -1, and the bottom is, what is this? Good, which is correct. What is this? Good, and that's it. So the limit is -1/2. Any questions? Okay, the last thing that I wanted to go over in this section before we move on is a theorem that is called the Squeeze Theorem. Okay, so let me explain the Squeeze Theorem before we look at a graph and before we analyze it and apply it in examples. Let's imagine that I have a function that is, let's say, maybe a parabola, something like this, opening upward. Let's say I have another function that is a sort of a parabola that opens downward. And let's say I have a function, so this is the parabola from above and this is the parabola from below, and let's say that near a point, near an x value, near a, I have a function that is squeezed between these two. Let's assume that that's possible. Okay. So I have a function above, I have a function below, and I have the middle function right here squeezed between these two. The theorem is also called sandwich theorem. Okay. Okay. So what if I tell you that the limit from above is 5 and the limit from below is 5? What do you think the limit from the middle function will be as x approaches that number? Not here and not here, right here at this number. What do you think the limit would be? Right? So when will this be useful? So what? If I know that a function is squeezed between two functions, where would it be useful? Here's when it would be useful. When I don't even have the function. So I have a function, f of x. We're going to look at examples in a second. So we have a function that is squeezed between two functions for any number greater than or equal to 0. And I'm asked to find the limit of this one, and I don't even have it. I don't have function f. I'm only told whatever it is, I don't care. It's squeezed between these two for x greater than or equal to 0. Find the limit as x approaches 4 from the function you don't have. So that is one application. But let's back up a little bit. Okay. So here's the idea. So let's say I have this function, which is f of x. Now let's say I have this function, which is g of x. And let's suppose I have this function, which is h of x. And of course, this happens near an x value, which is a. I don't care outside of this tiny open interval. I don't care what happens outside of the interval. But I know that near a, this is the situation. Two hypotheses. The squeeze theorem or the sandwich theorem has two hypotheses. The first hypothesis is this. The function I try to find the limit from is squeezed between f and g near a. Near a. What is the second hypothesis? That the limit of f of x as x approaches a from either side, and limit of g of x as x approaches a from either side, they exist. They exist, which means they are a number. Let's call that number L. And they are the same. Exist and are the same. If these conditions are fulfilled, then the squeeze theorem is applicable. And what will I conclude? What will be the limit of this function that I don't even have by the squeeze theorem? What will be the limit if all these conditions are fulfilled? I didn't mean f, I'm sorry. I meant h of x. So I know that h of x is squeezed between two functions. I know that the limits of those two functions they exist and they are the same. What will be the limit of h of x as x approaches a for sure? How much? Please.
The horizontal asymptote between the two.
No. So if this limit from left and right is L, and the limit of this function from left and right is L, and this function h of x is squeezed between these two functions, what could the limit of h of x be?
Is that f of x?
H. I changed it, I'm sorry. Yes, I made an error to write f. I didn't mean f, I meant h, of course. So I already showed you an application which we didn't work on yet. But I'd like to work on this function first, and then we'll look at that one. So that's the squeeze theorem. Any questions for me?